Little technical difficulty there. So an abrupt end to the previous video, picking back up with examples. So we know how to differentiate polynomials. Let's look at some examples. We know how to differentiate sums and so forth. So let's illustrate that with some mildly interesting examples. Here's a polynomial. W is a polynomial function of z, 3z to the 7th minus 7z cubed plus 21z squared. Let's differentiate it. So dw dz, if you like differential notation, that is the derivative with respect to z of w, showing off my differential notation and using some square brackets to indicate, to differentiate the stuff inside with the d dz stuff. More on square brackets here shortly. We get the following. Derivative of the sum is the sum of the derivatives. Derivative sum rule. So we can take the derivative of the first, 3z to the 7th, plus the derivative of the second, negative 7z cubed, plus the derivative of the last, 21z squared. Oh yeah, we can bring constants out front as well. So we can bring the 3 out front. We can bring the negative 7 out front. We can bring the 21 out front. So let's do that. And then we're just left with powers of z. You can do that by the derivative constant multiple rule. Funny thing, we never said, it's true, but we never said the derivative of the difference is the difference of the derivatives. That's why I had to leave the negative on the 7. It's true, and it's established with a derivative constant multiple rule when that constant's -1. But to precisely use the theorems that we have, I'll have to leave the negative on the 7. The computation is most important, more than that little subtlety. And now we need to differentiate z to the 7th. Okay, bring the 7 down front, subtract 1 from the 7. Differentiate z cubed, bring the 3 out front, subtract 1 from the 3. Z squared, bring the 2 out front as a coefficient, subtract 1. And there's a derivative, but let's clean it up a little bit. And we won't do them in quite this level of detail in the future, but this is our first one illustrating those rules. So we've got 21z to the 6th minus 21z squared plus 42z to the 1. And so this is what we get for the derivative of that polynomial function. Differentiating polynomials, piece of cake. Look, we brought the 7 down to get a 21 and subtracted 1 from the 7 to get a 6. Yeah, that's where the first term came from, and similarly for the other terms. So we'll speed this process up and start doing more complicated things quite soon. Second example, let r be a function of theta. And they're suggesting polar coordinates here, but whatever, they're just variables. R equals 12 divided by theta minus 4 divided by theta cubed plus 1 divided by theta to the 4th. We don't know what to do with division yet. We will soon. So we'll have to take care of that and differentiate it. All right, so we want to find dr d theta, the derivative of r with respect to theta. That's the derivative with respect to theta of what the r quantity equals. Derivative of the sum is the sum of the derivatives. We can bring any constants out front. The 12 comes out front. The -4 can be brought out front because of the derivative constant multiple rule. So bring the constants out front. What are you going to do now? You don't know how to deal with these quotients. Well, let's write these as powers of theta. This would be theta to the -1, theta to the -3, and theta to the -4. Because that's how you deal with negative exponents. You put them in the denominator and make those exponents positive. So we get this correspondence here. Do you know how to differentiate when you have a negative integer exponent? We've claimed we do. It's theorem 3.3.c, the general version of the derivative power rule, says bring the exponent down and subtract 1. Okay. So theta to the -1, bring the -1 down front, subtract 1. -3 exponent, subtract 1, -4 becomes a coefficient, subtract 1. Keep an eye on these. You're subtracting from negatives. So the exponent went from -1 to -1 minus 1, which is -2. -3 to -3 minus 1, which is -4. -4 minus 1 is -5. The exponents, they decreased by 1. And when you get practiced at this, you're going to want to reduce those exponents by 1. You are, but be careful when they're negative exponents. It doesn't go from 4 to 3. It goes from -4 to -5. So it looks like maybe it's behaved a little awkwardly. It hasn't. It's just the properties of negative numbers. But I've seen students make silly little mistakes when you've got negative exponents. Just be careful with that. And I don't know, there's the derivative. We could write it by taking these negative exponents and putting things back in the denominator, if you like, and write it in this form. So there's a derivative of that. We could do it because it's sums and constant multiples of things we know how to differentiate. What we know how to differentiate without having to go back to the definition are powers of the variable. How about this one? Well, this one's a little weird. Y equals x to the negative 3/5 plus pi to the 3/2. Take its derivative. dy dx is a derivative of that stuff. Derivative of the sum is the sum of the derivatives. How do you differentiate x to the negative 3/5? Bring that exponent out front as a coefficient and subtract 1 from it. How do you differentiate pi to the 3/2? This is why this one's kind of weird. Well, that's a constant. And they're trying to trick you, so you bring the 3/2 down 1 or something like down as a coefficient or something like that. But no, it's not a variable. It's just some number. It's a constant. Then its derivative is 0. So that's them being kind of sneaky bastards and trying to trick you with bringing the 3/2 down front and subtracting 1 or something like that. It's fine if it was a variable. It's not. It's a constant, and its derivative is 0. Bad test question. I intentionally put this one in the notes just to warn you of what they're up to here. That's a sneaky question, not a good teaching question, but keep an eye. It's in the book. Derivative of the constant is 0, so we get a 0 there. So we got negative 3/5 x to the negative 3/5 minus 1. It's be negative 3/5 minus 5/5. It's be negative 8/5, I think. We can write that in the denominator if you want. This is kind of in the format of what they gave us, so we'll leave it like that. Bring the exponent down and subtract 1. Piece of cake. That's at this stage kind of all we know, but we'll change that. Another example, does the curve y equals x to the 4th minus 2x squared plus 2 have any horizontal tangent lines? If so, where? Tangent lines. Let's see. Slopes of tangent lines are given by derivatives. That was the whole point of defining derivatives the way we did. So let's find the derivative of this function. Let's find dy dx or y prime. Derivative with respect to x of the function. Okay. Let's speed that up a little bit. That'll be derivative of x to the 4th will be 4x cubed minus 2 times the derivative of x squared is 2x to the 1. There's negative 2 times 2x leaves us with a negative 4x, combining the 2 coefficient and the 2 exponent that comes down as a coefficient, giving us a coefficient of 4 along with a negative sign, x to the 1. 2 is a constant, its derivative is 0, so the derivative is 4x cubed minus 4x. Let's speed it up a little bit. Work at your comfortable pace, but the notes are going to get a little quicker now. What are we going to do? We want to see where this has a horizontal tangent line. See, horizontal lines have slope 0. So we're really asking the question, where's the derivative 0? Here's a derivative. Let's factor it. That's how you find where functions are 0. Factor it and set the factors equal to 0. We can factor 4x out of this. That leaves us with x squared here and a minus 1 here, x squared minus 1. Ooh, difference of 2 perfect squares. We can factor that as well. So this factors to 4x times x minus 1 times x plus 1, where you got horizontal tangents, where that derivative is 0. So we'll set the derivative equal to 0 and solve for x. That is, we'll set y prime, 4x times x minus 1 times x plus 1, that we computed up here, set it equal to 0. That implies each of the factors, 0, yields a solution. So we could have x equals 0 from this factor, x equals 1 from this factor, and x equals negative 1 from this factor. X equals negative 1, 0, and 1 is where we'll get zeros. I've listed them in the order they appear on the real number line here. The order doesn't matter, but I'll choose to list them like that. So the curve has horizontal tangents at x equals negative 1, x equals 0, and x equals 1. That answers their question, but let's foreshadow some applications of derivatives. What are the points on the curve corresponding to -1, 0, and 1? That's easy enough. I just plug the numbers in. If I plug -1 into the original function, we'll get -1 to the 4th minus 2 times -1 squared plus 2. -1 to the 4th minus 2 -1 squared plus 2. And we get the point on the curve, -1 comma, whatever this is. Looks like it's 1. We get -1. This reduces down to 1. Yeah, it's 1 minus 2 plus 2. So the 2 and -2 cancel, and we're left with 1. Correctamundo. Plug in x equals 0. We get the point 0 comma 0 squared minus 2 times, 0 to the 4th minus 2 times 0 squared plus 2 reduces down to 2. We get the point 0, 2. Plug in 1, we also get out 1. So we get the points -1, 1, 0, 2, and 1, 1 as points on this curve. And in addition, when x equals -1, there's a horizontal tangent. When x equals 0, there's a horizontal tangent. When x equals 1, there's a horizontal tangent. By the way, oops, the domain of this function, it's polynomial, is all real numbers. Y prime exists for all real numbers, right? Here's a derivative, maybe you like this form better. That derivative exists everywhere. It's a differentiable function on the whole real line. I don't get what could go wrong, right? Division by 0, no division. Square roots of negatives, no square roots. Logs of negatives are problems. We don't have any of those problems. So this function is defined on the real line. It's differentiable on the real line. And you know these 3 points at which there are horizontal tangents. What I'm getting at is, just by taking this derivative and playing with it a little, you know a bunch about this function. This function's defined on the whole real line. It's differentiable on the whole real line. I'm going to draw a conclusion that differentiable means quote unquote smooth. Smooth's going to take on a technical meaning that's a little more involved than that in section 6.3. That's calculus 2. That's not the problem right now. So when you hear differentiable, it's not precise to think smooth, but I think you'll be okay to think smooth. There are some things that could go wrong, like vertical tangents, that are maybe a bit misleading in terms of this term smooth, but I'm using the term very informally. So when we draw this curve, it's going to be smooth. No vertical tangents, or the derivative wouldn't exist. So we know it is differentiable everywhere. The derivative was elementary. Also, the graph contains these 3 points because we figured that out. So we got a pretty good idea what the graph of this looks like, given the fact it's nice and smooth. It's got horizontal tangents at these 3 points and nowhere else. Bet you the graph looks a lot like this. So let's plot those 3 points, -1, 1, 0, 2, 1, 1. Here's the 3 points. It's got horizontal tangents. That's what the little hash marks indicate there. Horizontal tangents is those 3 points, and it's nice and smooth. And it doesn't have horizontal tangents anywhere else. It's got to look something like this. It must decrease down and level off right there. Turn around, go back up so it can level off there. Have a horizontal tangent at that point. Decrease, level off there so it can have a horizontal tangent there, and then increase. It can't wiggle around a bunch more. If it wiggled around more, it'd have more horizontal tangents, and the derivative would have told us about it. The only place it's got horizontal tangents is at these 3 points here. Does it have any sharp points in it anywhere? No, couldn't have any corners. The derivative wouldn't exist. If it had corners, that's one of the things that can go wrong with derivatives. And this one doesn't have any problems with its derivative. Its derivative is defined everywhere. It's differentiable everywhere. Some things I can critique. I got it coming down pretty sharply here and increasing pretty sharply over here. The information we have in front of us, I can't eliminate the fact that maybe it comes in really, really shallowly. Well, it does have to level off down here. Turn around and go back up. It couldn't increase and level off. Well, I guess it could. It could increase and level off and then increase some more. So I can't quite eliminate that with the information we have. We're this close to being able to analyze it more. So there's one thing I can't eliminate as well. There's still some details that I certainly can't eliminate. But broadly put, I think it looks something like this. We didn't find where the function is 0. If it increased up here and leveled off, it'd have to have a 0 somewhere over here. Either that or horizontal asymptote. And we know how to find some of these things. Some are just algebra, some are calculus things we've already done. But I claim the graph looks something like that. When x is big and positive, the dominant term is x to the 4th. And the function is going to be positive over here. It's going to be positive over here as well. This is what the graph looks like. But based on the 3 points and the horizontal tangents, I have a pretty fair idea just based on that of what the function looks like. There's certainly some more concerns I could have about the graph, and we'll throw calculus at it here I think in chapter 4. We'll apply differentiation to graphing functions. It looks like it's pretty useful for that in the information we got out of it right here. Back to the notes. Okay, this is one of my least favorite parts of Calculus 1 because of the way they're approaching it. We're going to make a claim, and there's what angers me so, without justification. We've done that with the generalized power rule as well. So a lot of it's coming in with the fact that we're using an early transcendentals version of this book. That means we get to the exponential functions pretty early on, is really what it means. We're going to differentiate an exponential function of the form f of x equals a to the x, where a is greater than 0, and I'm going to depend on some of your knowledge about exponential functions from the past. And I'm going to do something new and not justify it. So, my apologies. We want to differentiate this exponential function. Derivatives are, make it a little bigger, limit as h approaches 0 of f of x plus h minus f of x over h, because that's a definition of derivative. We're encountering a new function in the realm of differentiation, so we got to go back to the definition. F of x is a to the x, so what's f of x plus h? A to the x plus h. Minus f of x, minus a to the x. Okay, here we got an exponential function and we're adding exponents. Well, that's equivalent to multiplying with that common base, a to the x times a to the h equals a to the x plus h. Multiplication, common base, add exponents, so that's legitimate. We got an a to the x in both of these terms. So we could factor that out, factor it out, set it out front, leaving it in the limit for now. You can do that because that's just distribution. Hey, this is constant, ain't it? Well, it's got an x in it though. Yeah, but it ain't x that's changing in the limit, it's h that changes. So we can bring that a to the x out front. It doesn't depend on h. It's constant with respect to h, is how it's said. So the a to the x comes out front. And then we've got a limit as h approaches 0 of this thing here. Can you plug in h equals 0? Nope, because there's an h in the denominator. Can you factor this? You can't. If we could, we'd factor the numerator, factor an h out, cancel, and then substitute. But you can't factor an h out of that numerator. I want to say nobody can factor an h out of that numerator. There's a way to factor an h out of that numerator, but that way is based on something we're developing now. It involves introducing series. We mentioned series recently. So it's not something you can do until you do the series part of the book, chapter, I don't know, 8 or 9, maybe 10. In the calculus book. So for now, we're stuck with it. So what we're going to do is claim that this limit here exists, and it's some number dependent on a. And taking the lead from the book, they're going to call that number L sub a. All right, that pains me to say it, but that's how we're going to approach this. We're going to take this as given. We're not going to get to justify this. I think it's done much later. No, we'll get to do it. Good. It's in section 3.8. We'll actually see what that number is. It turns out that L sub a is the natural log of this value a. So we will establish that in section 3.8. This is developed a little more cleanly in a book that doesn't have early transcendentals. I've got notes out there from the 11th edition of this book. The 11th edition non-early transcendental versions. So there's links to some notes there if you really want to get into the weeds on the details. Let's just take it as given that what we're getting here is some number. Let's call it L sub A. We're going to make some speculation about its value as well. Up here we had, make it a bit smaller now, we had f prime of x written as a to the x times what we're claiming is some number called L sub A. Hey, what if you plugged in 0 for x? Then we'd have f prime of 0 equals a to the 0. A to the 0 is 1, unless a is 0, and we got a problem, and it isn't. In fact, a is positive. You only consider exponential functions with positive bases, and you don't use a base of 1 usually, so we haven't made that disclaimer. But a is not 0, so a to the 0 is 1. So we just replace that with a 1, and we get f prime of 0 is this limit, and it's this limit we're denoting L sub A. Yeah, this is related to log functions somehow or other. And I'm not surprised to have a conversation about log functions and a conversation about exponential functions because they're inverses of each other. But that's what that value turns out to be, to go ahead and tip my hand a little bit. More details to follow. Hey, but then this f prime of 0 thing, if it's a derivative evaluated at 0, it represents a slope of a graph because derivatives are slopes of graphs. So this f prime of 0, this L sub A thing, must be the slope of the graph of that exponential function at x equals 0. So we're going to have a figure, 3.13, and make some claims, again, kind of unjustified. This is the curse of using an early transcendentals book. If we were to graph exponential functions, so we graph y equals 2 to the x power, we get something like this. If we graph y equals 3 to the x power, we get something like this. So here's base a equals 2, base a equals 3, and what they're representing here is the slopes of tangent lines. It's not clear from the image, but that's what these numbers represent. We get a slope of the tangent line here of 0.69 when we take an exponential function, base 2. There's a remote possibility you might be familiar with approximating the natural log of 2 with 0.69. That number pops up if you have a background in maybe biology and you talk about exponential growth and doubling times of a population. If you talk about radioactive decay in a chemistry class and you talk about half-lives of radioactive decay, this number 0.69 pops up there. There's a chance you've heard of that. These other numbers, I doubt it. But trust me or trust the textbook, we get a slope of 0.69 approximately when we look at the slope of a tangent line for a graph of y equals 2 to the x power. Y equals 3 to the x power at 0, we get a slope of a tangent line of about 1.1. At base 2.5, graph 2.5 to the x power, we get a slope of 0.92. So it's getting close, somewhere between 2.5 and 3. That tangent line should have a slope of 1. So there's some graph, some exponential graph that passes through here that at 0 will have a slope of 1. F prime of 0 will be 1. It's a little less than 1 at 2.5. At 3, it's a little bit bigger than 1, somewhere in between. So I'm hinting at continuity here, an intermediate value theorem. I would expect the slope of that tangent line to be 1. So we're going to define the number e to be the number for which the slope of the line tangent to an exponential function base e is 1. So slope is 1 at x equals 0. That's how we're, and this is not much of a definition, but that's how we're defining this parameter e. In other words, if we took a limit as h approaches 0 of e to the h minus 1 over h, that L sub a thing, here we're replacing a with e, we'd get out a value of 1. That makes the number, again in section 3.8, we'll look at some of this, that makes that number e approximately 2.718281828459045 to, what's that, a dozen odd decimal places. And that's the base of the natural exponential function, and that's the base of the natural log function. What's natural about it? Well, it turns out it's a calculus property. It's a differentiation property. And remember, we chose that number e, scrolling back a little bit, such that we take f prime, well, we take f of x to be e to the x, then f prime of x is e to the x times this limit. And when a equals e, we said that limit's 1. That means, scrolling down, we've chosen e such that you take the derivative of e to the x, you get e to the x back, or e to the x times 1. That limit stuff we saw a couple of pages back, that's 1. That's how we chose the value e. So we get the derivative of the exponential function e to the x is itself. You probably dealt with exponential functions in maybe in chemistry with radioactive decay, or in biology with exponential growth. Exponential functions pop up in logistic growth in biology as well, where there's a carrying capacity. But maybe you've dealt with this function before, and why in the world they called it natural was not at all clear. Here's why they call it natural. If we differentiated any exponential function to a different base, that derivative would be way more complicated. It isn't complicated for an exponential function base e. The derivative of the exponential function is simply the exponential function itself. Details to follow in section 6.8. So we're adding this. It's not in blue. I don't have a proof of it. I just got some pictures and an argument and a long conversation. The derivative of this function is itself. So this is added to our repertoire of things we can differentiate. So we can easily differentiate with rules of differentiation, powers of x, and exponential functions. And that's all at this stage. We can't do logs. We can't do trig functions yet. We can't do inverse trig functions. There's a lot of stuff we can't. We can't even deal with products of functions yet. We'll take care of products here shortly. Let's introduce an example involving exponential functions. Okay, next example says, this is not a real involved one, differentiate f of x equals x plus 5 times e to the x. Okay, derivative of the sum is the sum of the derivatives. Theorem 3.3.e. We can bring that 5 out front. Constant multiple rule for derivatives, theorem 3.3.d. You got a power of x, you know how to differentiate that. Derivative of x is 1. You got an exponential function. What's the derivative of an exponential function? It's the exponential function itself. So we just get the e to the x back. Simplify, we get 1 plus 5 e to the x. Why didn't I differentiate the exponential function? I did differentiate the exponential function. It's its own derivative. The derivative of e to the x is e to the x. Back to the notes.